So we have been talking about gases, breakdown mechanisms in gases. Before I finish with gases, we must remember that the most commonly used gas insulator is of course air. And in terms of power transmission or power systems and apparatus, air is used as the insulator. So we are talking about air insulated systems or air insulated lines. Air is used as the most common insulator when we can make do with gases, is of course because air is abundantly available, it is free, and it is self-restoring after breakdown. So let's say in the transmission line, air breaks down. You have a single line to ground fault and air breaks down. All that you have to do, in case it's just the insulator which breaks down, you just have to wait for sufficient time to elapse and the air will regain its dielectric property. The charged particles will diffuse away, will be removed from the gap, and the air will regain its insulating property. There are, of course, international recommendations for air clearances when you need to design air insulated high voltage power lines and other equipments. For example, just to give you a couple of examples, when we want to design air for when we want to design the amount of air that is necessary for phase-to-phase insulation, we just have to provide adequate clearance let's say, between two phases of AC transmission line or between opposite poles of a bipolar DC machine. And if in the laboratory, either through experiments or through simulation, we want to figure out whether the kind of clearance we are talking about is going to be adequate, what we need to do is we need to use some models. And for phase-to-phase insulation, we would use a conductor-conductor model, which is parallel cylinders. So we might have two parallel cylinders in reality with scaled down magnitudes, or in the simulation, for example, if you're using the finite element software, you would simulate the phase-to-phase insulation with rod plane parallel cylinders or rod plane electrodes. Rod plane electrodes, when one is more planar, the other is not that plane, depends upon the dimensions. In the worst case, you might use a needle plane electrode. That is what I have been doing throughout my explanations, because this is the worst case scenario. And the needle plate electrode basically simulates a very sharp point on a conductor. The conductor in itself may be a parallel cylinder kind of conductor, but the sharp point is of interest because breakdown is going to initiate from that sharp point, and so that is the worst case scenario where we simulate the conditions with the needle plane electrode. Similarly, you can have the phase to tower or phase to ground insulation, where you want to figure out the insulation that you need to provide between phase conductor and the ground, or the phase conductor and the ground tower. And in this case, we would use conductor plane or rod plane electrodes. Of course, if we talk about air, are there any other kinds of insulation systems? We are more commonly using, or we are more familiar with the air insulated system, where you have transformers, you have transmission lines of the distribution network, and everywhere air is being used as the insulator, and it is just sufficient to provide adequate clearances. However, these clearances can become very large, and therefore your entire system may take up a lot of space. And this is not always a possibility when you have difficult terrain. Suppose you have to build your transmission line over a very mountainous region, and that means you have to clear ground. And if you have to clear a very large amount of ground, it may not be feasible. Or let's say you want your transmission line or your transmission network or your distribution network in a very populated area, let's say a city. You don't have the adequate clearances, and there is a chance of it being dangerous, the safety clearance is being violated, and it becoming dangerous to people. In which case, you would like to replace air by some other gas. One of the most common gases that are used in what we call gas insulated systems, we'll talk about gas insulated systems later, but that is SF6. I'll discuss later why SF6 is of importance, but we must remember that we do have gas insulated systems which do not necessarily use air. So this brings us to the end of gaseous breakdowns. Uh, Let me do a quick recap of what we have studied so far. We have first considered gas. We have considered the processes by which, on the application of electric fields, charged particles can be produced in a gas, because for a gas to go from insulating to a conducting medium, or for gas to break down, the first thing that you need is adequate quantities of charged particles. So we have talked about the various ionization processes by which charged particles are produced. We are also aware that there are processes which remove ions from the gas medium simultaneously. There are deionization processes like recombination and diffusion. Of course, we need to have enough ionization for breakdown to be there. In terms of gaseous breakdown, we have discussed two principal mechanisms. One is the Townsend mechanism, other is the streamer mechanism. The Townsend mechanism is the most basic and simplest to understand mechanism. It has to happen. You have to have an initiating electron, and that is related with the statistical time lag. And then you need the adequate time for the Townsend mechanism to build up such that enough electrons are produced, enough primary electrons are produced in the gaseous medium, enough secondary electrons are produced by positive ion bombardment and other secondary processes, and then all these two combine together to satisfy Townsend's breakdown criteria. Sometimes, if there is adequate enough of charge production, it may so happen that Townsend's breakdown mechanism will give over to, so it will start as a Townsend mechanism, but the mechanism will give over to streamer mechanism, in which case photoionization is involved, and therefore the breakdown will progress much faster than we predict through Townsend mechanism. And also it explains the zigzag lines that you see in a discharge, which cannot be explained using the Townsend's mechanism. Townsend's mechanisms and streamer mechanism are both relevant to breakdown in uniform fields. That means the entire gaseous medium sees a same constant electric field. With respect to uniform field, there is one more law that we have studied, and that is the Partitions Law, which gives us a minimum value of the product of pressure into distance of the gap at which the breakdown voltage is minimum. If you deviate from this PD product, either an increased value of PD or a decreased value of PD, either because pressure is increasing or because distance is increasing, then generally you will need a higher breakdown voltage. You will need a higher voltage to break down that gas in that gap than at the minimum value. So that is given by Partitions Law. But we do understand that it is not always uniform fields that we are interested in. Gaseous medium or any medium are often subjected to non-uniform fields, and when you have non-uniform fields, you have what are called partial discharges. Partial discharges is the localized partial breakdown of the insulating gas only in certain regions where there is local field enhancement. So there is no bridging of the electrodes, but there is losses because some part of the gas becomes conducting in nature. We've talked not about partial discharges, which we will discuss later in a different chapter, but we have talked about only one kind of partial discharge, that is the partial discharge that takes place in air. The partial discharge that takes place in air, and we are interested in when we are talking about transmission lines, because we very often see this in transmission lines, is corona. We've talked about the different modes of corona when you have positive polarity high voltage electrode and a negative polarity high voltage electrode. We've talked of the different mechanisms by which breakdown progresses either for positive polarity or negative polarity. We've talked about trickle pulses. We've talked about pre-breakdown streamers. We've also discussed why sometimes it is more common to expect breakdown to happen in a positive cycle rather than in a negative cycle. So with that, we will stop talking about gases and we will go on to talk about the other phases, the other kinds of insulation, liquids, solids, and composite insulations.